class, and welcome to lecture 5 of our course. In this lecture we're going to discuss gravity. We're first going to start by discussing the concept of a field, and then in particular gravitational field, and then we'll move on to Newton's law of universal gravitation, talk about how the inverse square law applies to the universal gravitation, and finally we'll end with talking about satellite orbits. So first we'll start with the concept of a field. Now, I'm sure in some sort of science fiction, literature, movie, or show, whatever you've heard like of a force field. Where force fields, maybe not as depicted in those shows, actually exist. Objects that have mass or electrical charge or magnetism, they set up force fields. In other words, they set up these fields in which they alter the space around them. And whenever they alter the space around them, that altered space, as a result, will exert a force on a particular object that possesses certain physical characteristics that are in that field. So for example, for gravity, the field set up by an object that has mass sets up a gravitational field that will exert a force on any other object that has mass in that field. Other objects that set up fields include objects with electrical charges. They set up electric fields. And there's also magnetic fields. And those fields can exert forces on objects, say an electric field. Anything that has an electric charge will experience a force from that force field that is set up by the other object that has electrical charge. So a field is how an object alters the space around it. Einstein told us that objects with mass, we can visualize it as the mass kind of warping space and time. It augments space and time by bending it, and that's how it alters the space around it. And so there's this concept of the field. This is how objects exert non-contact forces on other objects. It's through setting up a field. So anything that has mass sets up a gravitational field. And that gravitational field can then exert a force on any object that's in that field that has mass. And so moving on to, know what a field is, moving on to, in particular, gravitational field. Gravitational field is the field set up by any object that has mass. So a gravitational field, it's basically a force field set up by any object with mass. So the Earth sets up a gravitational field. You set up a gravitational field. The Earth's gravitational field is much stronger because it has a larger mass than the field that you set up. But nonetheless, you do set up a gravitational field around your body. Any object that has mass sets up a gravitational field. Now we measure the strength of that field as the force exerted on 1 kilogram of mass. That's how we assess the strength of a gravitational field. It's how much force would the gravitational field exert on an object with 1 kilogram mass at any particular location. And so we assess the gravitational force, the gravitational field strength as newtons per kilogram. How many newtons of force would be exerted on 1 kilogram of mass, or per kilogram. And so an object, it sets up a force field, and that strength, that force field varies with distance from that object. And And we're going to see how that varies with distance when we look at the law of universal gravitation and the inverse square rule. But at different locations, right, around this object, the gravitational field has different strengths. Different strengths measured in newtons per kilogram. So maybe this would be, the field would be weaker here than here, closer to the object. This would be a larger strength, so it would be more newtons per kilogram. All right, so this is how objects that have mass exert force on other objects that have mass by setting up gravitational fields. Now, to quantify what that force is, Newton actually found the relationship between the distance, so two masses, so let's say M1 and M2, they have two masses, M1 and M2, and they are a distance r from each other. Newton found that the force due to gravity that each object exerts on each other, well, first of all, I'm going to say that the force due to gravity, this is the force that object 2 exerts on object 1. So 2 on 1. So Newton's third law tells us that this force has to be equal and opposite. Force due to gravity of object 1 on 2. So Newton's third law tells us that these gravitational forces that they exert on each other are equal and opposite. So that's his third law. But his law of universal gravitation tells us how strong that force is. And so he found that the gravitational force that two objects exert on each other that have mass m1 and m2 is proportional to their masses. So the larger m1 is, the stronger the gravitational force that both of them exert on each other. The larger m2 is, the stronger the gravitational force that both of them exert on each other. So interestingly, if we increase the mass of m1, not only do we increase the gravitational force that m1 exerts on m2, but we also increase the gravitational force that m2 exerts on m1. It doesn't matter which mass you increase, the force on both of them increase because they're equal and opposite. And then the force is inversely proportional to the square of the distance between them. And so there's a proportionality constant here. And that proportionality constant is capital letter G, where G is the gravitational constant. It's a constant in the universe that we just find to be that proportionality constant in Newton's law of gravitation. And its units, what are its units? The value of G is 6.67 times 10 to the negative 11. It's a small number. And the units, what are the units? Well, force has units of newtons. So a newton is a kilogram meter per second squared. Now, we have mass times mass, so that's kilograms squared, divided by distance squared. So basically, what units do we have to multiply this by in order to get kilograms meters per second squared? Okay. So we have to the units of G are newtons, meters squared per kilogram squared. Alright, so you see that the kilogram squared cancels out this kilogram squared, the meter squared cancels out meter squared, and so the resulting units are newtons. Now we can also say, what is this in fundamental units? Well, a Newton is a kilogram meter per second squared times meter squared over kilogram squared. So the units of G in terms of mass, distance, and time are meters cubed over seconds squared kilogram. That would be, but we just write it, we're just writing G as newtons meters squared per kilogram squared. So that cancel out kilogram squared, cancel out meter squared, and left with newtons. Alright, so that's the units of G, so newtons, meters squared per kilograms squared. So this is just the constant of the universe. It's just, this is the value that is proportional to the proportionality constant between this force and the product of the two objects' mass, and divided by the distance between them squared. And so, as we said, as we increase either one of these masses, we increase the gravitational force. If we decrease either one of those masses, we decrease the gravitational force. And that's directly proportional. So if we double the mass, we double the force. We half the mass, we half the force. However, the distance between them, that follows the inverse square law, where the strength of the force, it falls off with 1 over r squared. So it gets weaker very rapidly as r increases. So if you double r, the strength of the force is reduced by 1/4. 1 over 2 squared, which is 1 over 4. If you quadruple r, if you increase the distance between two objects by a factor of 4, you reduce the gravitational force by a factor of 16. Right? So the inverse square law tells us that the force due to gravity falls off very quickly with distance. Right? So as you get further from, as the objects get further away, as r increases, the force due to gravity between them begins to fall off rapidly. Okay. So that if you are very far away, 1 over a very large number squared gives you a really, really small number, especially since G is already a small number, so the force due to gravity is tiny. So does Jupiter exert a gravitational force on you? The answer is yes. However, because we are so far away from Jupiter, we take that large distance and square it. And even though Jupiter has a large mass, and we have a small mass, compared to Jupiter, when you divide that large mass by that very large distance squared, and then multiply by a small number g, the resulting force is very, very tiny. It's pretty much negligible. So, does Jupiter exert a gravitational force on you? Yes. However, it's extremely small, so small that it's negligible. In theory, every object that has mass exerts a force on every other object that has mass, but those forces are just so tiny that they basically are negligible. And one of the reasons is because of this inverse square law. That the distance between them, as that increases, the strength of the force falls off very rapidly. Right, so us being so close to the Earth, r is small, right? R is basically, I have to say that this r is the distance between the centers of mass. So if we want to find out the gravitational force on us and Earth, this r is the distance between us and Earth's center of mass, which is the radius of Earth. So this distance is the radius of Earth squared. Which is a relatively small number, right, compared to like the distance between us and the sun, or the distance between us and other planets. And so that's why the force due to gravity of Earth on us is not negligible, because we're so close to the planet. So that's Newton's law of universal gravitation. And we'll look at some example problems where we use that to calculate the gravitational force between two objects. We'll also use it when we talk about satellite orbit. Now, I just want to look at this law of universal gravitation and look at the example as it applies to the Earth. Okay, so if we look at a person that's standing on the planet, like I said, the gravitational force of the Earth on the person is going to equal g, the gravitational constant, times the mass of the Earth, times the mass of the person, divided by the distance between them, which is the radius of the Earth, squared. And so, if we want to find what this gravitational force that the Earth exerts on a person is, we can see that, well, the gravitational constant is a constant. It doesn't change. It's a constant. The mass of the Earth isn't going to change, and the radius of the Earth is not going to change. So we can essentially just separate these terms out and find out what they equal. It should be a constant at the surface of the Earth. If we go above the surface of the Earth, we are increasing this value, right? We're increasing r, so this would be different. But if we assume that we're at the surface of the Earth, that should be a constant. Okay. So, what are the values of the mass of the Earth, radius of the Earth? So, just looking up quickly. So the mass of the Earth is basically 6 times 10 to the 24th. It's to be particular, it's 5.98 times 10 to the 24th kilograms. The radius of Earth is 6.37 times 10 to the 6 meters. And G is 6.67 times 10 to negative 11 newtons meters squared per kilogram squared. So what happens if we plug in this for the mass of the Earth, this for the radius of the Earth, and this for the gravitational constant, and we calculate that, we find that G times the mass of the Earth divided by the radius of the Earth squared equals 9.8, and the units are meters per second squared. Right. That's G. That's lowercase g. That's correct. That's lowercase g. And that's how we can easily calculate the weight of an object at the surface of the Earth. We're actually using Newton's law of universal gravitation. We're just, instead of calculating this every time, we're saying, oh, we're just going to assume that's a constant, that the mass of the Earth, plug in the values of the mass of the Earth, the radius of the Earth, and the gravitational constant, we get 9.8 equals G times the mass of the person, right? That's how we figure out the force through gravity of Earth on an object at its surface. We can just multiply its mass, the person's mass, or the object's mass, times the acceleration due to gravity. Right? And another way of looking at this is we can say that the force due to gravity of the Earth on a person divided by the mass of the person should equal the acceleration due to gravity, g. And so that's the force due to gravity of Earth on a person divided by the mass of the person, just like we're doing here. Sure enough, we get this value, g, capital G times mass of the Earth, the radius of the Earth squared. That's the acceleration due to gravity, g. Alright, so that's where that 9.8 meters per second squared comes from. And that's why it's It's 9.8 meters per second squared at the surface of the Earth. Once you go above the surface of the Earth, then this distance is no longer the radius of the Earth. It begins to increase, and this does not equal 9.8 meters per second squared anymore. It actually becomes less and less and less because you're increasing the distance. So if this is the Earth, and if you're up here, now you have to use this value of r, which is the radius of Earth plus whatever altitude you are above the surface. And so the force due to gravity up there on an object or a person would be radius of the Earth plus your altitude above the surface squared. And so that's going to decrease the force due to gravity. So the force due to gravity decreases with distance above Earth's surface, which makes sense because the force due to gravity drops off with 1 over the distance squared. It follows the inverse square law. Okay? So now we're going to apply Newton's law of gravity to a satellite in orbit. Now, in order to do this, we're also going to pull in a concept that we've talked about in our last lecture, which is uniform circular motion, because that's what a satellite is doing. It's moving in a circular path around Earth. And so, let's say that this is Earth, right? We're in the radius of the Earth, and we have a satellite. So the satellite is orbiting Earth, and let's say that this is ORB, that's the orbital radius. And so the orbital radius is equal to the radius of the Earth plus whatever altitude h it's above the Earth. But we're just going to simplify and say it's the orbital radius, which is measured from the center of Earth. Now we just can't put a satellite into space and say, go into orbit, right? We have to dial in the specific parameters for that satellite to stay in orbit. And we know all the physics as of now to do so. This satellite is going to be in uniform circular motion, to be in orbit. And so let's ask the question, well, if it's in uniform circular motion, it has a constant speed, right? And that speed, and so the magnitude of its velocity is constant, but its velocity is constantly changing direction. And so we know that what causes that change in direction is an acceleration. In particular, it's a centripetal acceleration. And what's causing that centripetal acceleration is some centripetal force. What is the centripetal force that's causing a centripetal acceleration? Well, it is the force due to gravity that the Earth exerts on that satellite. All right? So if we go over here and we look at the physics of, so the centripetal force, which is the force due to gravity acting on the satellite, is equal to the mass of the satellite times its acceleration, its centripetal acceleration. Now remember that centripetal acceleration is equal to the square of the velocity, so the square of the speed, divided by the radius of the circular path squared. Well, in this case, the radius is the orbital radius, right? The distance from Earth's center to the satellite. So we're going to plug that value in. And we're also going to plug in Newton's law of universal gravitation for the force due to gravity here. So we have g times the mass of the Earth times the mass of the satellite divided by the orbital radius squared. That's the force due to gravity of the Earth on the satellite. That's going to equal the mass of the satellite times the centripetal acceleration, which is v squared over r orbital radius. So the mass of the Earth is constant. We want this satellite to orbit at this particular distance. So the orbital radius is prescribed, right? We want this satellite to orbit at a particular radius.
The mass of the satellite is whatever the mass of the satellite is. It's the same orbital radius. You see that we have this variable here, which is the speed. So if we want a satellite to orbit the Earth at a certain altitude or a certain distance from Earth, we have to give it a very specific speed. That speed is dictated by the orbital radius,
Or vice versa, the orbital radius is dictated by the speed.
we just can't put a satellite in orbit at any velocity we want. If we solve this, well, first of all, we see that the mass of the satellite doesn't matter because it's in both sides, we can divide it out. Multiply both sides by orbital radius, cancel out that, gets rid of that. We see that the speed at which the satellite needs to be launched at, the velocity it needs to have, or the speed it needs to have, is equal to the square root of the gravitational constant times the mass of the Earth divided by the orbital radius. So that speed, if we look at the speed, it goes with 1 over the square root, right? So it's going to have, I don't know exactly what that looks like, but as it gets larger, it's going to be something like that, right? So the further away it is, the slower it has to. Further away it is, the slower it can travel. Now, what happens if we give it a velocity that's larger than this? If we give it a velocity for a given orbital radius, if we give it a velocity larger than this, that means the centripetal acceleration required is going to be larger than what the gravitational force can provide, and therefore it won't be in uniform circular motion. And the satellite will spiral off into space, and it'll just drift away from the Earth. If the velocity is less than this, that means the gravitational force is going to not only change the direction of the velocity, but it's also going to accelerate the satellite in a radial direction towards the Earth. And so instead of spiraling off into space, the satellite will spiral in towards Earth and then crash. That's in fact what happens whenever satellites are no longer being powered, because there is some resistance in space, and so every now and then a satellite needs a little bit of a thrust, a little bit of a force to accelerate it to maintain the required speed for a given orbital radius. And once it's no longer the systems are no longer working to maintain that speed, it slows down. And as it slows down, it spirals down and it enters Earth's atmosphere where it burns up, it breaks up and burns up. But if that system would malfunction and the thrusters start firing more than they should, and it gives the satellite a larger velocity, then what's prescribed by this? Then the satellite will spiral off into space. Now, another thing we can find from this is the orbital period, which is how long it takes the satellite to make one orbit. Because we know the speed at which it travels is the distance traveled, so it's 2 pi r, it's the circumference of the circle, divided by the time. Now capital T, we're going to say capital T is the orbital period. That is the amount of time it takes the satellite to make one orbit. Okay, that's the orbital period. And so if we plug this in for V, we get G, mass of the Earth, orbital radius, square root, equals 2 pi r or V over T. Okay, and if we want to solve for T, so say that we want this satellite to have a prescribed orbital period. we want it to take a certain amount of time to make one orbit. We solve for t, and that'll tell us what orbital radius the satellite needs to be at. We need to set it into motion. And so, well, first of all, we can just flip everything, divide everything by 1. So we get orbital radius over g times me square root equals t over 2 pi r orbital radius. And now multiply that over here. So we can put that inside this radical. So it becomes 4 pi squared. And we can put that in there. R orbital. So if we put that in there, that becomes a square. And so the square times this gives us cube over g times me. That's the orbital period. So the orbital period is a function of the orbital radius. In particular, it's proportional to 3/2 power, because the square root is to the 1/2 power, so 3 to the 1/2 power. So the orbital period is proportional to the orbital radius to the 3/2 power. And so this is a number greater than 1, so this is our orbital, this is d, it's something like this, right? So as the orbital period, as we increase the orbital radius, that's going to increase the orbital period. And so let's say that, oh, we're a telecommunications company, like a satellite TV company, and we want our satellite to orbit the Earth twice in a day, right? What orbital radius do we have to launch our satellite? Well, the orbital period would be, if we want it to go around twice in a day, that means it's going to take 12 hours to make one orbital period. So that's 12 hours. And so that equals 12 hours times 1 hour, 3,600 seconds. So we convert that to seconds. And we can just solve for orbital radius. That'll tell us what orbital radius we need to set that satellite into orbit, and you just solve this equation for this. So you get t squared times g and e divided by, well, we can factor out that it's just 2 pi all to the 1/3 power. Right, so whatever this is in seconds, plug that in there, and that'll give us the orbital radius. So what radius we need to put that satellite into space so that it goes around the Earth twice every day. If we want it to be once a day, this would be 24 hours. If we wanted to go around 3 times every day, this would be 8 hours, right? So we can, for whatever orbital period we want, that'll tell us what orbital radius that satellite needs to be put into orbit at. So at each distance from the Earth, we need a specific velocity for orbit. Because really what's happening is an object that's in orbit is in a constant state of free fall. But the rate at which it falls toward the Earth is the exact same rate at which the Earth curves away from it. So in theory, if this is the surface of the Earth, it's curved, we can launch an object right above the surface at a velocity so that as it falls towards the Earth, it's falling towards the Earth. You know, if we shoot an object, it falls to the Earth, but we shoot it fast enough that as it falls towards the Earth's surface curves away from it. So it's constantly falling towards the Earth, but the Earth just curves away from it, so it never hits the Earth. So it's in a constant state of free fall. So this idea of, you see pictures of people in the International Space Station or in the space shuttle that's in orbit, that they're weightless, right? They're floating around, they're weightless. They're actually not weightless. If they were weightless, they would drift off into space. They have a weight. That weight is the force due to gravity of the Earth on them. And that's what's allowing them to orbit, because it's the centripetal force that's providing this centripetal acceleration. If they actually had no weight, if there was no force due to gravity on them, Newton's first law tells us that they would just travel in a straight line. They just go on and on and on and on. Right? So they are, in fact, they do have a weight. So what they have is apparent weightlessness, because they're in the International Space Station or they're in the space shuttle that's in free fall as well. And so because their frame of reference is accelerating towards the Earth at the same rate they are, they're not pushing against it. And the only way we perceive our own weight is by feeling the force that the surface exerts against us. So I feel my weight by the Earth exerting a normal force up on me. And so let's say if the surface would start to accelerate upward, in order to accelerate me upward, the ground would have to exert a force that's equal to my weight and a little bit more up on me. So I'd feel a little bit heavier. And that's why whenever you step into an elevator and it starts to move up, you just get that brief sense of feeling a little bit heavy. That's that extra force that's beyond your weight that the elevator has to exert up on you to accelerate you upward. So you feel a little bit heavier. If you were standing on a scale, and if you were reading your weight, whenever that elevator starts to accelerate upward, that scale would tick higher a little bit. It would record a slightly larger weight. It's your apparent weight. Conversely, if you step into an elevator and it starts to descend, because the surface that you're standing on begins to accelerate downward, your weight would tick lower a little bit, because now the surface isn't exerting the same amount of force up on you, it's a little bit less. Now, imagine that you're going down the elevator and someone cuts the cable and the elevator goes into free fall, and you're standing on that scale, the scale would go to 0. Because you and the elevator car are accelerating downward at the same rate, acceleration of gravity, the scale does not exert a force up on you. Because that's the force that reads on the scale. It's the force it exerts up on you. And because you're both accelerating downward at the same rate, you don't exert any forces on each other, and your apparent weight is 0. Does that mean your weight is 0? No. You are accelerating down towards the Earth because you have weight. But your apparent weight is 0 because your reference frame, your surroundings are accelerating towards the Earth at the same rate as you are. So you're not weightless in space. You have a weight. If you didn't have a weight, you would just go off into space. But your surroundings are accelerating downward towards the Earth at the same rate as you. So you can't push against them. They can't push against you. Your weight isn't pushing against them. And so they're not exerting a normal force back, which gives us our apparent weight. We could reproduce this in an airplane too. You can feel weightlessness in an airplane if an airplane flies up, and if it starts just to go into a free fall. If the airplane is in a state of free fall, then inside the airplane you'll have a sense of weightlessness. Things will appear to float, and you will float relative to the airplane because you're both accelerating downward. And so that concludes our lecture on gravity. I'll have some example problems for this chapter that will work through some problems.